This is continuing the discussion. I just gave it a different title just to be distinguishing from where we left off. So we ended up by simplifying or transforming the system of the stratified atmosphere into this equation, d squared v dy squared, this coefficient times v equals 1 over c squared d mu dy minus k beta y divided by omega c squared times mu, where mu is our forcing function. We can transform it using this transformation so that d dy is square root beta over c d dc, and d squared dy squared is beta over c d squared dy squared. So we are using the meridional gradient of Coriolis and the gravity wave speeds to rewrite the equation in a more classical form, which is like a Schrodinger's harmonic equation. So you have d squared v d psi squared is this coefficient multiplied by v equals this function of forcing. Right? So obviously you can set mu equals 0 and create free solutions, or you can look at mu and see what oscillations are there in the system. So if you set mu y equal to 0 and look for solutions with a boundary condition that v goes to 0 at large y, we know that beyond the turning latitude the solutions are exponential and you can let it decay to 0 at some y. Then you get the free or unforced solution of this form with 0 on this side. Basically this term goes to 0. This is what is called a Schrodinger's harmonic oscillator equation. So in a general form it can be written as d squared d psi squared minus psi squared times v plus e times v equals 0. So if you are an expert on linear algebra and the whole eigenfunction business, then you know that E here is the eigenvalue E, which can be written as omega squared over c squared minus k beta over omega times c over beta. But you can see the meaning of eigen self being seen here. So you can think of it as a matrix times V equals an eigenvalue times V. Right? That's the transformation you typically think of. Matrix A times x equals lambda x, where lambda is your eigenvector. Eigenvector and eigenfunction are the same, but there are some differences in terms of eigenvector not being an eigenfunction, but eigenfunction being an eigenvector. All those nice things. What do we do with that? We can suppose that there is a family of eigenfunctions Vm, that's why I mentioned eigenvector and eigenfunction, that satisfy equation 5.549, this one. So V is, let's say, can be expressed in terms of family of eigenfunctions, sum over eigenfunctions m, with coefficient beta m Vm as a function of y. So we're just writing the meridional structure now in terms of this eigenfunctions, so that we can write the Schrodinger's oscillator equation as like this. Now we have the eigenvector or eigenfunction Em with the eigenfunction Vm. So here E is E as a function of omega, k, and h prime. So here c squared is gh bar, the average depth of the stratified atmosphere. Omega is in this equation. In this equation, omega represents a family of eigenvalues for a series of set values of k and the depth of the fluid h bar. So for the free unforced situation, Vm is the eigenfunction of the system, and omega is the eigenvalue for sets of k and h bar. Okay, so if you have, so we have to get used to the idea of free or unforced situation. It doesn't mean something is happening without any forcing necessarily. It just means that the forcing is applied and then it's removed and the system is set into oscillation, and then we see what the free solutions are in the system in terms of oscillation. In the forced problem, the equation, we have the full equation where again we are putting Vy in terms of the eigenfunction, a family of eigenfunctions Vm. Then the forcing itself can also be expressed in terms of the family of eigenfunctions, and write this relation of the E minus Em times Bm Vm as the sum of this complicated looking things, again Vm being the family of eigenfunctions relating to Vy. Okay, don't worry if you don't necessarily remember all these details. The equations are always there. When we go to physics, we'll keep revisiting these and interpreting the physics in terms of these forced and free modes. We'll get to see all of them. So in the forced problem then, the response is determined by the scale and the frequency of the forcing function. Okay, so the scale and the frequency of the forcing function is going to determine the response in this stratified system. So in this case, the forcing function sets the wave number and the frequency, and thus the eigenvalue for the force problem becomes h bar, the mean depth of the atmosphere that we are looking at. Okay, so using the orthogonal property of the eigenfunction Vn, we can write for a particular n, E minus En Cbn, as this complicated function again. Here now you have the orthogonality being used to write this Vn Vm plus this integral of Am over c square root beta c Vn dVm. Okay, we are not deriving these things, we are just showing them, so obviously it's not easy if you haven't been through these before or don't have an intuitive sense, and half the time I'm not even sure I know how to interpret all these things without the physics. Physics makes these things easier. That's why we are trying to get rid of these before we come to the physics, so that we can just focus on the physics and not get bogged down by the equations. So here C is given by integral of Vn deep psi, so that summed over all m we arrive at the general forced solution for the structure of Vy, which looks like this complicated monster. Okay, that's where we will kind of end it, the chapter. As we said, we'll keep looking at various solutions that emerge out of this formulation and these transformations. But basically what we have done is started with Laplace's shallow water equations that he developed for tides, and we put various conditions on them and created shallow water equations for the ocean and the atmosphere with and without background flows. We did some linearization and looked at various wave solutions. We defined turning latitudes, saw this tropical region as a potential well in that context, and we will see what that means in more detail later on. And then we developed this stratified atmosphere to basically show that forced and unforced solutions can be very different. Also, when you look at the ocean, in the ocean we assumed a homogeneous water column, but we had boundaries and we had reduced gravity. So for the ocean we needed this upper ocean structure with the quiescent deep ocean below that. So even when you have divergence in the upper layer, the deep ocean is not set in motion because it's too deep. Okay, so those kinds of details will matter when we look at these things, but it's clear that we have a stratified ocean, stratified atmosphere, so the horizontal and vertical modes are tightly coupled. So we will see how that gives us the baroclinic processes that we were talking about in the atmosphere, and the role of the ocean in these coupled modes, and how ocean itself has got these vertical and horizontal modes. Okay, it's going to be very nice physics, so no need to get too concerned with the equations. Just read the chapter, look at the equations, just be comfortable with them. No need to panic.